The origin of replication is represented here with the template DNA laid out. The origin of replication is where replication begins. There is one origin of replication in prokaryotes, and there are many in eukaryotes. It's important because it shows where replication begins, and it is useful to determine the replication direction. 3' to 5' is the direction of the template DNA for the leading strand. This is why it can have continuous replication. DNA replication occurs from the 5' to the 3' end. Although I'm only showing the leading strand here, this is also the direction it occurs in the lagging strand and the reason that Okazaki fragments are formed. The leading strand in DNA replication is represented here. The leading strand is created through continuous replication of the DNA template strand. The lagging strand is represented here. The lagging strand is created by discontinuous replication. It has to be discontinuous in order for replication of the DNA to occur in 5' to 3' direction. These little pieces are called Okazaki fragments. I will be using these small pieces of string from the template for the lagging strand to show Okazaki fragments. Okazaki fragments are small pieces of replicated DNA that are created by discontinuous replication that form up the lagging strand. I will use this pretzel to represent ligase. Ligase seals the new strands of DNA by repairing nicks, which also helps to join the Okazaki fragments. I will be using a Cheerio to represent gyrase. Gyrase relieves tension due to supercoiling upstream of the fork. It is also in the family of toposomerases. I will be using a piece of popcorn to represent helicase. Helicase unwinds the DNA double helix, which allows the DNA to be replicated. We'll be using these triangle cutouts to represent single-stranded binding proteins. Single-stranded binding proteins, or SSBs, bind to the single-stranded DNA to keep them separated and in place in order for replication to occur. I will be using this elbow noodle to represent RNA primase. RNA primase lays down the RNA primer, which provides a starting point of replication. I will be using this sticker to demonstrate DNA polymerase III. DNA polymerase III attaches to the primer and adds nucleotides to it. I will be using this sticker to demonstrate DNA polymerase I. DNA polymerase I removes the RNA primer and replaces it with a segment of DNA. Phosphodiester bonds are represented here by small pieces of the spaghetti noodle. Phosphodiester bonds are important because they join nucleotides and overall forms the sugar phosphate backbone of DNA. Here we can see the completed prokaryotic replication fork, leading strand, lagging strand, ligase holding to the Okazaki fragments, DNA pol 1 and 3 adding and replacing onto the RNA primers, SSB, helicase, and gyrase, keeping the strands in place, and phosphodiester bonds to create the backbone of the new replicated DNA.